Hi, and welcome to a lecture on minimum variance array processing. There's three things you should know about MV right up front, and those are, first, it is the primary alternative to Bartlett array processing. Bartlett array processing having been discussed in a previous lecture. For beamforming, MV amounts to adaptive null forming. And thirdly, for angle of arrival estimation, MV yields resolution which is superior to and dynamic range which is superior to Bartlett processing. However, these advantages come with new pitfalls. So to begin, let's begin with a quick review of array processing in general, regardless of algorithm. So what I'm about to repeat here applies to both Bartlett and MV processing. First, we have the concept of a steering vector. The steering vector is the element response to a plane wave instant from the direction in which the vector r hat points. The formalism I have been using for this is to say that the elements of the steering vector are given by the product of the element pattern for the associated element in that direction, times a factor which accounts for the array geometry, where beta, as always, is the phase propagation constant, p sub n is the position of the nth element, and r hat, once again, is the direction which we are currently considering, from which the plane wave arrives. You stack them in an n by 1 vector and you get the steering vector, which is a complete description of the array's response to a plane wave arriving from the direction r hat. The beamformer output is written as follows. The output is y as a function of time. X as a function of time is the snapshot vector. That's the n by 1 vector of element outputs, in other words, the data. And b is the n by 1 vector of beamforming coefficients. And the convention we're currently using is that the beamformer is defined as b Hermitian, that's conjugate transpose, times snapshot. So the output is a scalar value. The power received from direction r hat, as measured by the beam b, is given by this expression s as a function of r hat, which is the correlation of the beamformer output with its conjugated version, which we've shown in another lecture to be equal to the beamformer vector Hermitian times the spatial covariance matrix times the beamforming vector again. Recall that the spatial covariance matrix is simply the outer product, that is, the snapshot times its conjugate transpose, integrated over some period of time t. Alternatively, if you have digital data, you would normally express the spatial covariance matrix as the sum of outer products taken for each one of those sampling times. You just sum over L of them and then divide by L to get an average. It's just the digital version of the integration. From this we can write the angle of arrival estimation problem statement, which again is true for any algorithm, is that we're looking for the direction which maximizes the power output from the beamformer. And that's given by the spatial covariance matrix, left and right multiplied by the beamformer vector in the associated direction. Now for Bartlett processing, the beamformer vector is simply the steering vector. So it's the simplest thing you can imagine doing. Some might refer to this as unconstrained beamforming. Some people might refer to this as max gain beamforming. And some refer to it as Bartlett beamforming. These terms generally mean the same thing. In this case, the angle spectrum, that is S as a function of look direction, is given, as always, by the spatial covariance matrix, but in this case, left and right multiplied by the steering vector, because the steering vector is the beamforming vector in the case of Bartlett processing. So, to start off with an example that we can use for comparison later, here's the Bartlett angle spectrum for a particular problem. Here we have a 16-element uniform linear array with half wavelength spacing and isotropic elements, just to keep everything as simple as possible. So the search domain is over phi going from -90 to +90, and phi equals 0 being the broadside direction. If we have a signal incident from 30 degrees and no noise, so the only thing the array sees is the signal, then we get this sync-like response, which is the Bartlett angle spectrum. And I should also point out, this may or may not have been discussed in a previous lecture, that in the case where you have that same angle of arrival, that same signal arriving from a particular direction, in this case 30 degrees, and you also have noise, and in this case we'll consider the noise to be spatially white, that is, the same noise incident from every direction which you look, then what happens is you get an angle spectrum that looks more like this, where those side lobes are muted somewhat, because as you scan that beam in azimuth, or along phi, you also receive some noise, and so that noise blunts the nulls that you would ordinarily see. Now the limitations of Bartlett processing, at least two of them are indicated here. One is resolution. So now what we're doing is that we still have the original signal incident from 30 degrees, but now we have an additional equal power signal, which is 5 degrees away, incident from 35 degrees. And we see that the effect of this is pretty severe. Whereas before, when we only had the one signal at 30 degrees, now we have a widened lobe in the angle spectrum, and the side lobes are washed out as well. But the main issue here is that we cannot tell by looking at this that there are two signals. It's not exactly clear what's going on. Maybe it's one signal that's a little bit wider. Maybe it's two signals. Maybe it's something different. The point is that we are no longer certain what's going on here. Whereas in the original case with one angle of arrival, we would see that the main lobe has the anticipated shape. When the main lobe does not have the anticipated shape, it's hard to know what's going on. The second major limitation is dynamic range. So here we have once again the same signal incident from 30 degrees with the same strength and the same noise, but now we have a second signal. And the second signal is incident from 10 degrees away, phi equals 20 degrees. And in this case, I'll make the signal 20 dB stronger. And what we see in this case is that the angle spectrum is completely dominated by the stronger signal. In fact, if we look at this and we did not know in advance what the signals were, we would clearly believe that there was a signal incident from plus 20 degrees, but we would not necessarily be aware, we would have no evidence that there was a second signal incident from plus 30 degrees because it's more or less obscured by the stronger signal. So we refer to this as a dynamic range problem. The stronger signal limits the ability of this processing to see the smaller signal of interest, and which would otherwise be detectable. The MV strategy aims to overcome these limitations. So, first a preface note, MV is also known as MVDR, MVDR standing for Minimum Variance Distortionless Response. In yet other places, you'll see this referred to as Capon or Capon processing. That's a reference to one of the people associated with the early development of MV techniques. The MV problem statement for finding the beamformer vector is the following thing. We are looking for the beamformer vector which minimizes the angle spectrum. And we want to do that such that the beamformer output in a specified direction, namely the direction specified by the steering vector, is 1. So let's examine those two pieces. The first part here, we are trying to minimize output power. Now note that Bartlett processing was almost the same thing, except saying max output power. The min here was a max in the Bartlett processing problem statement. So we're trying to minimize power. In fact, that's what the term MV is referring to. Variance is power. So we're trying to minimize output power. But see, we can't just do that, because if that was the whole problem statement, the answer would be simply to set B, the beamforming vector, equal to 0, because that would set the power output to 0. So to keep that from happening, what we do is we introduce a constraint. And this constraint is with respect to a particular direction. And so this will keep the processing from simply turning coefficients off, because if it turns coefficients off, it won't be able to satisfy this constraint. So this constraint is the thing which specifies the current look direction, if you will, in the angle spectrum. So the problem statement says minimize output power overall, but don't mess with the response in a particular direction, namely that specified by the steering vector A here. And this prevents the trivial solution that you just turn off the beamformer entirely. This is an example of constrained optimization. So some people refer to MV as being a constrained beamformer. Now, written this way, this is a straightforward problem in linear algebra. And the solution to the problem is that the beamforming vector is equal to the inverse of the spatial covariance matrix divided by this factor here, which is the inverse of the spatial covariance matrix left and right multiplied by the steering vector. This particular set of beamforming coefficients is then referred to as the MV or MVDR or Capon beamformer. And good time to note the difference with respect to Bartlett processing. Recall in Bartlett processing, the beamforming vector was simply the steering vector. And here we obviously have something more. In fact, note right away that it depends not only on the steering vector, but also on the data. We'll come back to that idea at the end of this lecture. The angle spectrum for MV processing can be determined as I've shown here. Here's the angle spectrum for any type of processing, which can be expressed in terms of a beamforming vector. But now we'll substitute the expression for the beamforming vector. So we have the spatial covariance matrix, left and right multiplied by the beamforming vector. And we have many factors here, but this reduces in a fairly straightforward way. First, note that the Hermitian of the inverse of the spatial covariance matrix is just the inverse of the spatial covariance matrix. And that's because the spatial covariance matrix, as well as its inverse, are conjugate transpose versions of each other. That is, the spatial covariance matrix and the inverse of the spatial covariance matrix are both equal to their Hermitian. So the Hermitian has no effect on the inverse of the covariance matrix. So what we get when we take the Hermitian of that numerator is simply the inverse of the spatial covariance matrix left multiplied by the steering vector. And here everything else is left the same. So now when I take all the factors that appear in the numerator and line them up, I see that there is a place where I have the inverse of the spatial covariance matrix right multiplied by the spatial covariance matrix, and that is the identity matrix. So those melt away, and I'm left with the inverse of the spatial covariance matrix left and right multiplied by the steering vector, which is what I have in the denominator squared. So this whole thing boils down to the angle spectrum being equal to 1 over the inverse of the spatial covariance matrix, left and right multiplied by the steering vector. Once again, good time to compare to the Bartlett angle spectrum, which is simply the spatial covariance matrix, not its inverse, left and right multiplied by the steering vector. Okay, now time to do some examples. Same conditions as before, an n equals 16 element uniform linear array, half wavelength spacing, isotropic elements, and we will keep that spatially white noise. That spatially white noise is really important for MV processing. I'll return to that idea at the end of this lecture. For the first scenario, where I have simply a signal incident from 30 degrees, phi equals 30 degrees, blue shows Bartlett processing as before, and we have the sync-like spectrum, the blue curve. And now we're showing the MV result as a red line, and you will see immediately that the performance is dramatically better. We see a very sharp spike at the angle from which the signal is incident, and furthermore, we see that the MV spectrum is flat at all other directions. Unlike the Bartlett spectrum where we have the side lobe structure. So low uniform response where there is no signal present, and that's a pretty big advantage of MV. If we consider the resolution challenged scenario from the previous set of examples, that is where we had signals incident from both 30 as well as 35 degrees, and in this case are equal power. Once again, the blue curve is Bartlett processing, and we had that problem that Bartlett processing just kind of smeared out the result and did not resolve the signal into two different peaks. In contrast, MV processing still retains this low, flat noise floor and clearly resolves both peaks. In fact, it resolves them and correctly identifies them as being equal power. In the dynamic range challenge scenario, same one where we had a second signal incident from phi equals 20 degrees and 20 dB stronger, where Bartlett processing obscured the second signal, or allowed the second signal to be obscured in the side lobes created by the first signal. What happens in MV processing is we get two sharp spikes, exactly what we'd hope to see, and furthermore, they have the correct peak levels. Here 0 dB and plus 20 dB. So once again, MV resolves both signals despite the 20 dB between the two signals, and still the MV noise floor is quite flat. We say approximately unbiased. So why does this work so well? Well, the MV beamforming vector, that is B, has a null in the direction of any signal not specified by the constraint, because that's what it takes to minimize the variance as we requested in the problem statement. So how does it know to put a null in the direction of any signal that is not currently of interest? Well, it knows to do this because we gave it the data. The data is a spatial covariance matrix. And this is unlike the Bartlett approach, where the Bartlett approach does not have access to the data. So this is a true example of adaptive nulling. The MV beamforming vector is, in fact, an adaptive nulling beamformer. What could possibly go wrong with MV beamforming? Seems like everything is turning up roses here. Well, you need to watch out for a few things, and let me identify those so that you know to look for them. First, MV has problems with multipath. Multipath is spatially distinct but correlated signals. Spatially distinct means arriving from different directions, and correlated means they came from the same transmitter but took different paths to get to the array that's doing the processing. So this is a problem because multipath signals, these correlated signals, can be described as a single steering vector even though they come from different directions. And that typically does not go well in MV processing. Second, MV is generally less robust to calibration errors. So, for example, small errors in the array manifold, small errors in the steering vectors can dramatically affect the nulling performance. By the way, this is a problem that's shared by most systems that try to do nulling. If you don't give it an accurate model for the array, that is its element patterns and the element positions, it will typically have a hard time putting the nulls in the right place. Finally, high signal-to-noise ratios can lead to poorly conditioned, or we say low effective rank spatial covariance matrices. In order to invert any matrix, it has to have full rank. And if you have inadequate amount of noise, that is a signal-to-noise ratio which is too high, then inverting the matrix will be problematic because it'll be trending towards a singular condition. So for example, MV tends to have problems in jammer scenarios where the jammer might be crazy strong relative to the noise that would ordinarily be seen by the processor. But this can show up in all kinds of problems. To avoid it, there is a technique known as diagonal loading, which is artificially adding noise to the spatial covariance matrix before you do the processing. But that's a topic for a different lecture. To summarize, the smart play is always to do Bartlett processing also. That is, if you're going to do MV processing, I would recommend you also do Bartlett processing. And the reason is because Bartlett processing has a relatively low computational cost. Compared to the effort it takes to do MV processing, the additional effort to do Bartlett processing as well is usually negligible. And the advantage of Bartlett processing is that even though it's limited in many respects, it's not affected by the same issues as MV processing, namely multipath, sensitivity to calibration errors, and this low effective rank problem. So Bartlett and MV have complementary strengths and weaknesses, and it usually makes sense to do both. That concludes this lecture on minimum variance array processing.